goodness, guys, guess what?
What?
I just invested the best $12 of our college careers. Yeah. Yes. Well, the point is, if the zombie apocalypse ever comes, we'll still be able to tell time.
You've got a point. But where are the potatoes?
That's a good point. I don't know. Since we're poor college students, we don't really have potatoes.
Cafeteria has fruit.
That's a good idea. Let's go.
Well, 3 bags of fruit should be enough.
Yes. A lot of fruit.
This away. Alright, so let's get this thing started.
Let's see. It says we need a potato and this package.
And we do not have the potato.
But we have this package.
Let's just go with what we have.
Okay.
So according to the instructions...
Ah, screw the instructions.
Okay. It's your $12. We hook this in here. There. They should be the opposites.
Yeah. And that goes there.
This should go right here. Great. Let's see if it's... Oh, it's on. It really works. That's neat. But why does it work? That's the question.
I don't know.
So we did some research on electrochemistry to help explain why the orange clock works. And here's what we found. A galvanic cell, also known as a voltaic cell, also known as battery, is basically our experiment in its simplest form. And here's how it works. There's an anode, a zinc anode, and a copper cathode put into solution containing ions. And the cathode solution contains a copper ion, and the two are connected by a salt bridge, which allows for the exchange of ions. The negative ions go into the zinc solution, and the positive ions go into the copper solution. So, a redox reaction explains how the electrochemical potential is produced. At the anode, zinc solid undergoes oxidation to become zinc 2+, and then it gives off 2 electrons. At the cathode, copper 2+ is reduced, so copper 2+ plus 2 electrons becomes a copper solid precipitate. So to explain that, as zinc 2+ goes into solution, 2 electrons are given off and go along the current and go to the copper cathode where where reduction takes place, and the copper ion in solution precipitates to the cathode. Now the salt bridge maintains charges so that this reaction can continue to take place. So as the zinc 2+ ion is given off, the negative ion will come into this solution, and as the copper 2+ precipitates and the electrons come into solution, the positive ion will go into this solution. Alright, so now to explain what's going on in the orange experiment. It's a similar deal. However, we have no bridge between the two, and copper is not actually being reduced. Oxygen from the air comes and meets at the cathode with the electron transferred from the zinc, and the oxygen is reduced to hydroxide. And we've drawn the reduction equation right here. O2 plus water plus 2 electrons becomes 2 hydroxide ions. And so in solution, the zinc 2+ ion and the hydroxide minus ion maintain the charge, much like the salt bridge did in the galvanic cell. Now, let's go back to the lab and see this in real time with oranges. Onward.
now we're going to demonstrate what we just showed on the whiteboard. Here we have our oranges. We have our two sets of electrodes set in a series. And I'm going to plug them in and demonstrate how it works. And the clock should be on now.
Yep, it is.
Okay, so what is going on here is that the zinc anode is being oxidized from zinc solid to zinc 2 plus. 2 electrons are flowing through the circuit, thus powering our clock. Oxygen from the air is going into the slit at the copper cathode and is reducing, and the 2 electrons are reducing this oxygen. They're forming OH, as we saw in the whiteboard. Since these 2 electrodes are close enough together, the zinc 2 plus in solution and the OH negative in solution can exchange and equalize the cell's charge, thus acting as a salt bridge.
Using this information we have now acquired, we are now going to bust the myth of the potato clock by showing that it does not matter what you use in place of the potato, that we can use oranges, apples, water, for example, to conduct this experiment equally. And to prove that there really is very little difference in the ion transfer that takes place, we can use a voltmeter to test differences between these systems. So we'll do that now. Now, connecting this circuit with our voltmeter, we can test the voltage going through the circuit, which turns out to be about 1.5 volts. We can now use the same procedure with our other forms of salt bridges. Similarly, the apples produce a similar voltage of nearly 1.5. And finally, the water also produces a voltage of nearly 1.5 volts.
To conclude, we have learned that the potato is not necessary for the potato clock to function. All that is necessary is a salt bridge, something that allows the hydroxide ions and the zinc 2 plus ions to be transferred. That salt bridge can come in the form of an apple, an orange, a cup of water, just anything that will allow the salt ions to be transmitted.
Well, do you still think it's worth those $12?
Of course, I mean, if the zombie apocalypse ever comes, I can just take any old bucket of water and we can power a clock or a flashlight. So, yeah.
And for the knowledge we learned, it was money well spent.